Hi there, Miss Barber here. The title of this lesson is Continuity. Continuity is often used to describe the behavior of the graph of a function at a point or over an interval. A common informal description is a function is continuous if the graph of the function can be drawn without lifting your pencil. That is, the graph continues indefinitely in both directions from where you lay the pencil on the graph or without a break on a specified interval. In calculus, we will formally define continuity using limits. We will begin this lesson with an algebra refresher on finding the domain of functions. So example 1.4.1, find the domain of the functions. Part A, f of x equals the quantity 5 minus x divided by the quantity 6x plus 2. Let's observe that in a rational function, we are only concerned with what makes the denominator equal to 0. So the requirement would be that the denominator of 6x plus 2 cannot equal 0. Let's solve for x. So 6x cannot equal negative 2, and x cannot equal negative 2/6, which reduces to negative 1/3. We write this in interval notation as from negative infinity to negative 1/3 union negative 1/3 to infinity. Let's look at part B. G of x equals x squared plus 3x plus 2. We have two algebraic restrictions to consider when looking at the domain of a function. One is something in the denominator, and the other is unacceptable values under a square root. This is a polynomial function with neither of these things, so the domain is the entire number line, an interval notation that's negative infinity to positive infinity, or you could just as well express it using the mathematical symbol for the set of reals. And part C, h of x equals the square root of the quantity 10 minus 2x. In the real number system, we do not work with imaginary values, so the requirement is 10 minus 2x must be equal to or greater than 0. We're okay with having a 0 under the square root, just no negatives, so let's solve. We've got 10 is equal to or greater than 2x. Let's divide by 2 on both sides, so we get that 5 must be equal to or greater than x. I prefer to see the x on the left-hand side, so I will write this as x is equal to or less than 5. So in interval notation, that would be negative infinity 2, and the number 5, use a bracket because we can include the 5. In example 1.4.2, we will still continue with some more algebra refreshers. Determine which, if any, of the graphs are continuous. The informal definition is that we can draw the graph without lifting our pen. So for the first graph, we appear to have a split somewhere in the first quadrant and the fourth quadrant. In fact, it's probably clear that we have a vertical asymptote splitting the two pieces of the graph. And because you have to lift a pen, we will say that this is not continuous. Now let's look at the second graph. Let's note that it does have a sharp point in the third quadrant and also again in the first quadrant, but sharp points are nothing to do with continuity. We can still continue to draw from the descending line to the increasing part of the curve, and we can also draw from the increasing part of the curve into the first quadrant, where the direction of the curve changes, but it is still continuous. So we'll say this graph is continuous. And the last graph is often called a step function. As you can see from the graph, it has little segments starting in the third quadrant, moves up a little bit, and now we have a portion in the second quadrant, one that starts with a positive x-axis, and finally another segment that's in the first quadrant. Because of the breaks, we say that this graph is not continuous. Now that we have reviewed the algebra approach to continuity, let's explore the calculus definition of continuity. Continuity. We say a function is continuous at x equals a if all of the following are true. 1. The function exists at a. 2. The limit as x approaches a of f of x exists. And 3. The limit as x approaches a of f of x equals the function evaluated at a. A function is continuous over an open interval a comma b if it is continuous at each point in that interval. If the function is not continuous at x equals a, we say that it is discontinuous. We have some continuity properties for specific functions that makes it a little bit more straightforward to determine. 1. Polynomials, including constant and power functions, and exponential functions are continuous everywhere. 2. Rational functions are continuous on their domains. That means everywhere except where vertical asymptotes or holes exists. 3. Radical functions such as a square root function and log functions such as the natural log of x are continuous on their domains, and piecewise functions with continuous pieces can only be discontinuous at the ends of their intervals. Example 1.4.3. On what intervals is the function f of x equals x cubed minus 4x plus 17 continuous? Let's recall that f of x is a polynomial. F of x is a polynomial function. And by the properties we just learned, we know that polynomials are continuous everywhere. So the interval from negative infinity to infinity, or if you prefer, we can denote the set of real numbers with its symbol. The polynomial is continuous on the real number line. Next example, 1.4.4. On what intervals is g of x equal to x plus 3 quantity divided by x minus 5 quantity continuous? This is a rational function. The only point or points of discontinuity is where the function either has a vertical asymptote or a hole. In this instance, we will have where the function is undefined, where the denominator equals 0. So we'll say g of x is undefined at x minus 5 equals 0. Solving, we get x equals 5, and so the interval notation would be negative infinity to 5, not including 5, union 5 to positive infinity. This notation picks out x equals 5. Some completed examples. Example 1.4.5. On what intervals, if any, is h of x equal to the cube root of the quantity x plus 4 continuous? Since the domain of a third root or any odd root is all real numbers, this function is continuous from negative infinity to positive infinity. And exercise 1.4.6. On what intervals, if any, is the function f of x equal to the fourth root of the quantity x plus 4 continuous? F is only defined when the radicand is non-negative, so we must choose that x plus 4, which is the argument under the square root, is equal to or greater than 0. When solved, we get the interval with bracket because negative 4 is okay. We can have a 0 under an even root. So bracket negative 4 to positive infinity. Example 1.4.7. Determine if the following functions are continuous at the specified points. Part A. g of x equals the piecewise defined function 3x minus 5 for x strictly less than 2, and 2x plus 1 for x equal to or greater than 2. We are asked, is this piecewise function continuous at x equals 2? Remember, the requirement is the function must be defined at that point, the limit must exist at that point, and the function value and the limit value at x equals 2 must be the same. So let's begin with, does the function exist at g of 2? For g of 2, we use the second piece because the restriction is x is equal to or greater than 2, so we evaluate 2 times 2 plus 1. That is 4 plus 1, so yes, the function does exist, and that function value is 5. Now, to determine whether or not a limit exists, we must determine both the left-hand and right-hand limit. So let's compute the limit as x approaches. Let's do 2 from the left first, of g of x. From the left means numbers less than 2, so we'll use the piece that's the first one. 3 times 2 minus 5. That'll be 6 minus 5, and the left-hand limit is 1. Now let's look at the limit as x approaches 2 from the right of the function. From the right means numbers greater than 2, so we'll use the second piece, which will be 2 times 2 plus 1, 4 plus 1, which is 5. We observe that the left hand and the right hand limit are not the same, so we can conclude that the limit as x approaches 2 of g of x, and we'll write does not exist. Do not use the empty set symbol here. And we're sufficient. As long as one of these three is not satisfied, we can say it is not continuous, and we don't need to do any more work. Now part B. Is the function described as r of x equals the rational expression x squared minus 9 all divided by the quantity x minus 3 if x does not equal 3, and the second piece equals 6 for x equals 3. Is that continuous at x equals 3? Let's use the definition of continuity. We are first concerned with, does the function exist when x is 3? Yes, it is defined as if x equals 3, then the function equals 6. Second piece. And that is, does the limit exist? And so we've got a couple of things to consider. And on this one, we don't approach from the left or the right because we're just concerned with whether or not the limit exists. So we want the limit as x approaches 3, but does not equal 3, for x squared minus 9 divided by x minus 3. When we compute this, we end up getting 0 over 0. Remember, this means indeterminate, which means you can't tell, but the directive it is do something else. So we will do something else. We'll factor the limit as x approaches 3. Let's factor the numerator. X squared minus 9 is a difference of squares, so that factors to x minus 3 times x plus 3. The denominator is still x minus 3. The x minus 3's cancel. And again, since we don't care what happens at 3, we're not concerned with a whole right now. And let's simplify this to take the limit. The limit as x approaches 3 of the remaining term, x plus 3, that's 6. So one more thing remains to prove, and that is, does the limit as x approaches 3 of r of x equal the function defined at 3? And the answer is yes, they both equal 6. So we can conclude that this function is continuous at x equals 3. Part C. Is h of x continuous at x equals 0 if h of x equals 1 divided by x squared? Remember the 3 steps required for continuity. The first is that the function must exist at the specified point. 2, the limit must exist at the specified point. And 3, the function value and the limiting value at the specified point must equal the same value. If the first 2 do not work, then there's no need to continue. Let's begin with the first step, and that is the function defined at 0? Actually, this is undefined. At 0, the function's denominator is 0. It is undefined. Since the function does not even exist at that point, there is no need to do the remaining steps. We conclude that h of x at x equals 0 is not continuous. Exercise 1.4.8. Use the provided graph below to answer the questions that follow. The description of the graph. The graph is located on an xy plane with the vertical asymptote of x equals 2 drawn with a dashed line. The 2 pieces are: the first, reading from the left, is an increasing line located in the 3rd quadrant, terminating at the origin with an open hole. The second piece begins on the positive x-axis at 2. It is a curve that decreases, has an open hole at the ordered pair 1, 1, continues to decrease towards negative infinity as it approaches the sketched vertical asymptote. Part A. The limit as x approaches 0 from the left of f of x. Let's repeat. With the limit, we are not concerned with what happens at the value, but what happens near the value. In this instance, we are approaching 0 from the left, which follows the graph of the line, and that line function value approaches 0. Let's look at the limit as x approaches 0 from the right. In this instance, we are looking at the curved figure. As x gets closer and closer to 0, the graph itself reaches the completed circle value, which is the function value of 2. So now let's consider finding the limit as x approaches 0 of f of x. Even without referring to the graph, we see that from the left and from the right, the limits have different values. So we say that the limit as x approaches 0, that's from both sides, does not exist. Now let's look at the limit as x approaches 1 from the left. As x approaches 1 from the left, we are still looking at the curved graph, and it approaches the open hole on the graph, which is the function value of 1. Now, if we look at the limit as x approaches 1 from the right, as we get closer and closer to 1, even though from the right, even though the open hole is there, that is also the function value of 1. And since the left hand and right hand limits are the same, part F, the limit as x approaches 1 of f of x, which means from both sides, is still 1. Now let's look at the function values. Part G, f at 0. And at 0, when x is 0, the graph has a closed circle at x equals 0, which would be the function value of 2. And at f equals 1, so we want the function value at 1, it's an open hole. The left hand and right hand limit exists. The limit value is the same, but the function itself does not exist. Now let's look at the limit as x approaches 2 from the left. The graph appears to show that it is getting smaller and smaller and smaller. In fact, it is approaching negative infinity. Now the limit as x approaches 2 from the right. It does not exist. There is a vertical asymptote we have at x equals 2 and no graph at all to the right of x equals 2, so we say that the limit does not exist. Let's continue. The question now, part K, Is the function f of x depicted in the provided graph continuous at x equals -1? So if we look at x equals -1, it is. It's completely drawn through there, so graphically we see that, but we also notice that the limit as x approaches -1 from the left and the right approach the same function value, and it is also the actual function value, so we say that it is. The limit exists as x equals -1 exists. It is equal to the function value at 1, and my best guess looks like it's about -1/4, and so that works. Part L. Is f of x continuous at x equals 0? The graph itself tells us it is not continuous because we have a gap. To provide, according to the definition, we will say that the limit as x approaches 0 from the left of f of x, which was 0, is not the same as the limit as x approaches 0 from the right of f of x. Since the limit does not exist, so we'll say since the limit as x approaches 0 of f of x does not exist, it is not continuous. Let's continue. M. Is f of x continuous at x equals 1? So we'll look at x equals 1. Let's recall that the limit did exist. We have that the limit as x approaches 1 of f of x exists, and we denoted that to be 1. However, the function itself at 1 does not exist. And since the function value itself does not exist, we conclude that it is not continuous. And let's do n. Is the function continuous at x equals 2? The answer would be no. First, you can view that graphically. There is a vertical asymptote. So in algebra, that would be sufficient. In calculus, we would say that the limit as x approaches 2 from the right of f of x does not exist. Furthermore, the function itself at 2 does not exist. So I'll use this notation, which looks like the endpoints of an equilateral triangle. It is read, therefore, we will say that f of x is not continuous at the specified value, which was what? X equals 2. The intermediate value theorem. Let f be continuous over a closed, bounded interval. If z is any real number between f of a and f of b, then there is a number c in that closed interval satisfying the equation f evaluated at c equals z. This property is often used to find zeros of continuous functions. Recall that a zero is an x value which evaluates the function as 0. That is, z is a 0 of f of x if and only if f of z equals 0. Example 1.4.9. A continuous function f of x has the following values. F of 1 equals 5 and f of 4 equals -3. What does the intermediate value theorem say about zeros between the values of x equals 1 and x equals 4? Let's begin this by looking at a possible sketch of this f function. I'll draw a grid. It's the xy plane. And what I am given is that at x equals 1, the function value is 5. So we have an ordered pair in the first quadrant. And at x equals 4, the function value is 4, -3. So we have a point in the fourth quadrant. If it is continuous, that means to get from the ordered pair 1.5 to 4.-3, you cannot have a break. So whatever it's doing, it has to cross the x-axis. So what we can say is that for this given criteria, f of x has at least one zero value between x equals, let's see, 1 and x equals 4. Example 1.4.11. If f of x is continuous, what is the minimum number of zeros on the closed interval from 1 to 10 based on the intermediate value theorem for the table of values presented? The answer is equivalent to the number of sign changes between successive x values. So let's note, we have a sign change between x equals 3 and x equals 4. So that's 1 0. We have a sign change between x equals 4 and x equals 5. That's another change. And we also have a sign change of the function value between x equals 5 and x equals 6. So that's 3. The next sign change we have is between x equals 7 and x equals 8. So that's 4. And then we have one more sign change between x equals 9 and x equals 10. So we have a minimum number of zeros based on this graph of 5. Completed example. Please reference your student notes template for the completed example of exercise 1.4.12.